Hello and welcome to the second tool session webinar of Databrix. I am Tarmo Luumann from GuardTime, and today we are looking at tools that help us keep the data trustworthy. As you know, Databrix project aims to provide a holistic, energy-efficient and user-friendly toolbox of practical, robust and scalable solutions. And Databrix toolbox is governed by GenPlane methodology. There is a number of tools that can be used by arranging them into workflows. All the tools are Dockerized for easy use, and tools can be accessed by APIs. So when using Databrix tools, the GenPlane data governance process is what we go by, and according to GenPlane, the tool use is divided into 8 disciplines and 4 phases. Today we are looking deeper into a tool from the Azure discipline. So this tool is called Data Integrity and provided by GuardTime. And I will now hand over to Arto Truu from GuardTime as he will give us a deep dive into the Data Integrity tool.
So, hello, and thanks for the introduction and welcome to this session. As Tarmo already explained, I will talk about protecting data integrity with a technology called KSI. And what is KSI at a glance? So it is a blockchain-based cryptographic timestamping service, which can be quite a mouthful if you are not working in this field every day. So let's go a little bit facet by facet to understand what it means. So a cryptographic timestamping service the goal is to provide proof of time and integrity of some data. And KSI in particular provides independently verifiable proofs of data integrity. So when a data item is timestamped, the timestamp can later be used to prove that the data has not changed since it was timestamped. It also, KSI also provides the same timestamp token from KSI also provides independently verifiable proof of registration time. So it can be verified when the data item was timestamped, and this establishes a time during which you can prove that the data was not changed. Of course, the data may have been in the same shape or form also a long time before the timestamping event took place, but the proof cannot, the timestamp cannot prove that. So the timestamp covers the time from stamping until verification, and it is possible to show that during this time the data item was not changed. These two properties are required properties of any cryptographic timestamping service. In addition, KSI also provides a forward secure attribution of data origin. This is again a bit of a mouthful. What it means in plain English is that the token also records which client of the KSI service requested this particular token. So this can be associated that whoever requested the token on this data, the timestamp token on this data, it can be implied that this party also was in possession of the data. Otherwise, how could they have stamped it? And so this is an attribution of data origin. It is not quite as strong attribution as by getting a digital signature. It is more like a witness statement that the service gives to the client, that the service has witnessed the client having access to this data, but it lacks the property of non-repudiation that is deemed necessary for signatures according to the European law at least. So it's somewhat weaker than digital signature, but still provides some information about where the data comes from or where it has been. And a key property of KSI timestamping service, separating it from some others, is that long-term verification of those proofs of data integrity and registration time, they are independent of keys or other secrets. So there is no risk of service provider's password or private key leaking, and this affecting the verification or evidentiary value of your timestamps that you have already obtained. Also, when we speak about cryptographic timestamping service, often people assume that KSI provides encryption service. This is not the case. We use cryptographic tools and techniques to provide timestamps, but timestamping and encryption are separate activities in cryptography, and KSI is not the data encryption scheme or data encryption service. Also, despite being blockchain-based, KSI is not a cryptocurrency, which is also a common misconception when anything related to blockchain is mentioned in any context. So just to get those two things cleared out up front. And now let's go and have a further look exactly how KSI works and what it provides. So KSI as a timestamping service is built on top of hash functions, cryptographic hash functions. These are deterministic functions which map arbitrary inputs into fixed size outputs. And the outputs are fairly small. A typical size of a hash function is a few hundred bits, which means a few tens of bytes. So it's compared to most input data, the hash values are much smaller, and they serve as a digital fingerprints of the original or underlying data. And cryptographic hash functions are required to have several security properties. The two most important ones from timestamping point of view is that they are one-way. So given a hash value, it is impossible to recover the original input from that hash value alone. So they are, in a sense, privacy protecting. And they are collision resistant, which means that it is infeasible to find distinct inputs that map to the same output. And this means that the hash value or the digest or fingerprint, it is known by many different names in the field, can be used as a representative of the original data. There is a verifiable link between the data and the hash. And if you think about the fingerprints of humans, and most of the properties of how humans and fingerprints are related to each other, they carry over. So just like it's impossible to recover the original data from the hash value, it is also impossible to recover the human from the fingerprint. And just as it is possible to verify when you have a fingerprint and a human in front of you, it is possible to verify that they match, that the fingerprint really belongs to the human and not to some other person. The data and its hash values, they also have these relationships that if you have both of them in front of you, it is possible to verify that they do match indeed. And in fact, one of the first actually, the first known way of timestamping data without disclosing it was based on a hash function of sorts. Galileo Galilei did it back in 1610, when he wanted to claim priority on a discovery he had just made without disclosing what the discovery is. So he wrote down his discovery as a short sentence and scrambled it, and published the scrambled version in a newspaper, so that he would later be able to show the unscrambled version of the statement, and the appearance of the scrambled version in the newspaper would prove that the unscrambled version, he had it before the newspaper was printed. So he would be able to prove then that he had this idea, but he would not at the same time have to disclose the idea before verifying it further or working on it further. Robert Hooke from England was another scientist who used similar methods a couple of decades later. So this is actually a very old idea of using publishing hash values to establish a time of some data without disclosing the data itself. And the same idea was rekindled again in early 90s with the advent of and invention of modern hash functions. The ones used by Galileo Galilei and Robert Hooke, they are very, very weak functions by today's standards. So both from integrity and also from confidentiality viewpoint, it would be easy to break the security properties of those hash functions using modern techniques and modern technology. But in 1990s, people invented hash functions in the modern cryptographic sense, and started also reinventing the idea of how to use those for timestamping. And the basic idea of hash and publish or hash linking based timestamping is that the hashes of data items are registered in this kind of sequence or chain of blocks, chain of records. And each record or each block includes also the hash value of the previous block. So when a number of items is published, hash values is published, then in the next iteration of the work of the timestamping service, the hash of the previous block is included, and then the hashes of the new data items are added to this, and this forms the current head of the blockchain, and this continues growing like that. And then for any hash value included in any of those blocks, it is possible to verify which block it is included in, and because of the hash links, the order of the blocks is protected. So blocks cannot be changed after their hashes have been included in the following blocks without breaking the hash link, and they also cannot be reordered. So the integrity of this blockchain data structure can be verified, and then following that, the position of the hash value in this block can be verified, and this can be used as an evidence of the time when this item was entered into this kind of digital ledger. And this is a basic idea of hash linking based timestamping, which cryptographers have been investigating since late 80s, early 90s, from the last century. And one problem with this kind of direct inclusion of all the data in the blockchain is that it does not scale very well. All the data has to be either all the data or at least the hash values of all the data items that need to be timestamps. They need to be included in those blocks. And it's if the service gets a lot of use, if there are many clients, the blocks can grow big, and the whole ledger can grow big, and it is difficult to maintain, and it in general becomes unwieldy, inefficient. So an idea was proposed also in the 90s to aggregate the data hashes and include in this linked chain only the summary aggregate values. And the idea is to use a data structure called a hash tree or a Merkle tree to do the aggregation. So now instead of adding the hash values of individual data items that were timestamped into this block record directly, what is done is that the hash values of those data items are entered into the leaf nodes of a binary tree, and then those two neighbors are hashed together to produce a new hash value. And because of the properties of the hash functions that irrespective of the size of the inputs, output is always of fixed size, this hash value here, even though it now represents twice the amount of data, it is still of the same size as each of those input values. And this can be done iteratively in many layers until however large is the input set, it eventually is guaranteed to converge into a single summary hash value that indirectly represents the whole set. And this one single hash value representing the whole set is then included in the ledger. And a property of this hash tree, which I will not go into too many details here, is that for each of those inputs, a compact proof, essentially a chain linking this one input to the root hash value that was included in the ledger, can be extracted from the tree. So for each member, an independent compact inclusion proof can be provided, which shows that this one element was part of the set here that was aggregated to produce this root value, and this root value in turn was linked into this chain, establishing the time when this aggregation took place. So this gives this is now a two-step process to obtain a proof of when this element was included in the ledger. But it's still, after those two steps have been verified, it provides a strong cryptographic proof that the data existed at this time when this block was created in the ledger, and the data has not been changed after that, which is the goals that we wanted to have from a timestamping service in the first place. Now, to make this service even more scalable, what KSI does, and this is in fact an innovation by Guardtime in this space with our KSI product, is that this aggregation tree that collects the inputs from clients, the inputs may be from different clients, and aggregates them into a hash tree. This process is distributed among many servers, so we are not limited by how many requests in one round one server can process. And this is done by splitting the tree into layers. So normally, if we assume that one server can collect, let's say, eight inputs and produce a small hash tree of the 3 layers from those inputs, then how we can combine those smaller hash trees into bigger ones by having a second level of aggregation, which collects only the root hash values from the first level of aggregation and aggregates them further to obtain a second level tree, which links together those first level trees. And the data structure here is that it still provides a hash link chain from any of those leaves into this intermediate node. And this can go on for several more layers. And in general, the KSI system architecture is built up of 4 layers. And each of those nodes here can actually build a tree of 1,000 or more leaves. So we get to the with the 4 layers, we get to the point where we can aggregate billions of inputs from different clients, billions of inputs from thousands of clients in every round, and the load of this computation is distributed across many servers, and new aggregators can be added into this aggregation network when the load grows. So when we get to the point where we already have 1,000 clients here, which is what the second level, 1,000 aggregators here, which is what the second level aggregator can support. We just add here one more second level aggregator, and can then, under this second level aggregator, can add another 1,000 first level aggregators and connect new clients, new customers to those. So this service is, for all practical purposes, this service is infinitely scalable. We can just add more hardware, and there is no architectural bottleneck in how many data items we can process in each round, in each second. The duration of the round in KSI service is 1 second. So this aggregation tree is built every second, and proofs linking each client's input to the corresponding root value are returned to clients every second. So this is aggregation tree is built and from scratch every second, and in the next second, in the next round, a new tree is built from the new requests received from clients during the next round or next second. And this tree is built, and those trees kept being built every second, and linked together into what we call a hash calendar. So those blue trees here now on this figure are the aggregation trees, which can contain billions of leaves. Each of them, they have been computed in this distributed manner to distribute the load among multiple servers. But eventually, whatever requests for certifying or registering the data items during 1 second have arrived, they result in one single hash value, which, as explained here, should then go into the ledger and be linked together with the value from the previous round, and then be included also in the summary value in the next round, and so on. Now, the next thing is that if this aggregation and this ledger building occurs every second, then the ledger itself gets a new node every second, and to trace the history through the ledger also becomes a sizable task after the service has worked for a while. So in a day, the service produces 86,400 new records in the ledger, because this is how many seconds there are in a day, and in a year this adds up to something like 32 million records, because this is how many seconds there are in a year. And now, to make this processing of this linked list of rounds more efficient, instead of a linked list, we use another tree. So normally, according to the slide 2 slides back, these elements here should be linked into a linear chain, and then verifying the integrity of this chain, or in particular, I don't, as a customer, I wouldn't care about verifying the integrity of the whole chain. I only want to verify or prove the integrity of this element which my data links to. I don't care about others. And in order to be able to provide those, to support this efficient verification of individual elements instead of linear linking, we build another hash tree on top of this data, on top of those round summaries. And this second hash tree, which replaces the linear linking, we call a calendar hash tree. And you can think of it roughly, if you have a database table, then to find some data in it, or to verify the existence of some data in it, you would have to scan the whole table. And then to make this process more efficient, database systems build indices on the table. So there is an index, which is a supplementary information next to the data table itself, which helps with quickly locating the data, or quickly verifying that some data item is not present in the database. So the binary tree, the hash tree built on top of those of this linear list of inputs, serves roughly the same purpose in the KSI system, and we build the tree in such an incremental manner that every now and then, more specifically on the 15th of every month, we can take the root hash value, current root hash value of the tree, and publish it in a physical newspaper. This way, we are able to provide a tangible physical evidence that can be used to verify the integrity of the database, of the digital database, of the digital ledger, even in case that guard time ceases to exist, and the KSI service as a service is not operating anymore. So this is a very, very strong guarantee of long-term evidentiary value of KSI timestamps for our customers. The security of those timestamps depends, it links to physical evidence, and it depends on the cryptographic properties of the hash function, which is one single primitive that needs to be cryptographically strong. And there is no need to rely on guard time maintaining privacy of some signing keys, or maintaining privacy of some passwords, or anything like that. So this is the reason why we do those newspaper control publications. They can be used to audit the service and to verify the integrity of timestamps against tangible evidence. And the index on top of those aggregation rounds, this is built incrementally. Every second a new round is executed of aggregation, a new element is linked into this tree, and then at the next 15th of a month, the next incremental publication is generated, which logs all the new entries that have been added to the ledger since the previous publication, but also all the previously existing elements. So the publications cumulatively, each one covers a longer time span than the previous one. Everybody covers the whole time span since the service was started until the moment when this publication was generated. So they are incremental. And any of those timestamps can be linked to any of the publications that have been made after this timestamp has been issued, and both the time and the integrity of the timestamp can be verified against this publication. And now, how all of this mathematics is deployed in practice. This is infrastructure part. So the infrastructure consists of several layers. At the top of the infrastructure is a so-called core cluster, which maintains the hash structure. So this is a purple hash tree, the calendar structure, which is a purple hash tree from the slide. And this is maintained by a distributed cluster of servers. The cluster here is not for load balancing or for performance reasons or load distribution. The clustering here is for availability and reliability. The amount of computation needed to maintain this hash calendar is really quite small. Only one hash value is added into this calendar hash tree every round, every second, and adding and linking this new hash value into the index only takes a few tens of hashing operations, which are very cheap. A regular laptop can do a few million operations, hashing operations every second. So there is really no need to have a cluster of servers to do those few tens of hashing operations every second. So it is the cluster here is only to provide service availability, so that the clients would not lose service when one of those servers is either disrupted or is taken down for regular maintenance. Other servers continue providing service to users. So we can do maintenance on the core machines without any downtime of the service for any of the clients. So, and the goal of the core cluster, or the role or function of the core cluster, as said, is to maintain the hash calendar only, and also to produce those summary values for printing, for publishing, which we publish in print media, in newspapers, for really providing very strong tangible evidence, physical evidence, but we also, for convenience, we distribute it in electronic form as electronic media. So the same values that we print in newspapers, we also distribute as a digital archive for convenience. So people can implement verification of timestamps using automated tools, which do not need to go to the library to fetch a newspaper to do the verification work. They can do it based on digital copy of the same information. And then here is the aggregation network. We already mentioned that the one function of the aggregation network is to collect the inputs from clients, and then collectively across the network distributes a load of building the hash tree, the new hash tree of all client requests every second, and submitting the root tree for inclusion into the root of this aggregation tree for inclusion in the calendar. Another secondary function of the aggregation network is distributing the calendar database. Again, the purple nodes here, which basically implements a function of linking the ledger together to provide the history of changes. So distributing this back to the client computer. So every client has a copy of it. When they need to verify integrity of any of the timestamps they have, they don't need to go to the core cluster to ask for the reference. They have the reference cached locally. And the client-facing part of this service is what we call a gateway server, which basically includes a local aggregator and a local copy of the hash calendar. So the client has all of this available on their own premises. Both aggregator networks that we maintain, all of this is redundant. None of the computers here are single points of failure, and also the gateway server can be deployed in a redundant configuration, so that a client who needs high availability of this service, they can deploy multiple gateway servers in parallel and then take them offline for maintenance one by one without disrupting the service to the final applications. And for integrating all of this, the requesting of the timestamps and also the verification of the timestamps, for integrating this into applications, We provide APIs for many popular programming languages, most notably C, Java, the .NET platform. We have written the API in C#, but it can be called from any .NET platform language. And we also have libraries in Go and JavaScript available to be integrated into client applications. So this is for those clients who want to integrate KSI timestamps into their own information systems, into their own products or their own data management tools. And we also have some ready-made tools for handling storage and logging. So you can just, for example, if you use rsyslog, a popular software package for logging on Linux, if you use this to manage your logs, system logs on your Linux servers, you can enable KSI timestamping of those logs with just adding a couple of lines into the configuration file of rsyslog. These kinds of integrations have been built on top of the service using the APIs, and any developer can use APIs to do similar integrations into their own tools and products. And this pretty much concludes the presentation. So as a summary, KSI is a blockchain-based cryptographic timestamping service. As any timestamping service, it provides verifiable proofs of data integrity, verifiable proofs of data registration time. And these are, because the system uses this hash linking-based technology, these are independently verifiable. Another common way of doing timestamping is by having the service provider just provide a written signed statement that this data was presented to me at this time. And then everybody who wants to verify the timestamps, they can verify that the signature on the timestamp is valid, and then they have to trust that the service provider has included correct date and time in this claim. With hash linking based timestamping services, the hash linking is a functional causal relationship between events, and there is a lot less trust required in the service provider. So this is what we mean by saying that the KSI timestamps are independently verifiable. You can verify it for yourself. You don't have to trust the service provider. The attribution of data origin, the inclusion of information about which client requested any particular timestamp token is still trust-based. So the server verifies that the client has client authentication before issuing the timestamp and includes this information in the token. The information, you cannot verify that the information was correct to begin with, but the client identity is included in the token in such a way that it cannot be tampered or changed after the fact. So the attribution is trust-based, but the integrity of attribution is verifiable. It is forward secure. It cannot be changed after the fact. Once the timestamp token has been issued, the client identity in it is also cryptographically protected and cannot be changed anymore. And because of the hash function-based implementation of the service, the long-term verification of KSI timestamps is independent of keys or other secrets. So it is verifiable purely based on mathematics. No keys or passwords or other secrets need to be trusted to be still secret and secure. And also because it is built on hash functions, it is resistant to known quantum attacks. So most digital signature systems in use today are known to be vulnerable to attacks to forgery of signatures by quantum computers. Hash functions can be, the attacks against hash functions can be a bit more efficient with quantum computers, but the reduction of security is modest and can be countered. And this is the basis for claiming that hash functions are resistant to known quantum attacks. There is no mathematical proof that no quantum computer or no quantum algorithm to attack hash functions can ever be found. but so far no attacks against hash functions or no devastating attacks against hash functions with quantum computers are known. And as a perhaps a final bit of information, KSI is a eIDAS qualified timestamping service, eIDAS qualified trust service. And as far as we know, it's the first and so far the only blockchain-based eIDAS qualified trust service. So another small point of innovation here, which hasn't happened before. And that is what I wanted to say today. Thank you for your attention, and back to you, Tarmo.
Thank you, Otto, for a very thorough presentation. Now we have time for some questions. So you can either use the raise the hand tool and ask your question yourself, or write it into the questions function. Some questions have already been posted, and let's take a look here. Now, one question: is there a maximum file size limit to using this technology?
Not really. The hash functions, cryptographic hash functions, they are designed to take basically unlimited size inputs. There is some really high limit, for example, for the SHA-2 family of hash functions that we are using. The length of the data in bytes is also included in the computation, and this is a 64-bit unsigned integer, which means that the values that can be stored is 10 to the power of 18. So this is a lot more. This is several orders of magnitude more than the total amount of information available on all the IT systems on Earth, and really several magnitudes, or several orders of magnitude with spare room. So for all practical purposes, there is no limit. You can hash data of any size. You can produce a fingerprint and submit the fingerprint to the timestamping. And you don't really, one thing that I'm not sure if I mentioned in the presentation, you don't move the actual data to the timestamping service. You only send in the fingerprint. So no matter how big your data is, your request for timestamping, it is very small, a few hundred bits, a few tens of bytes. And your data, first, it stays on your premises. So this is very confidentiality preserving. And it is also very efficient. You only send a small amount, a small request out. You receive back a small response, a few kilobytes, and that's it. You don't need to shuffle the data itself around.
Okay, and you mentioned already efficiency. One question we have is about that. Basically, someone is asking, I heard that blockchain-based tools waste huge amount of energy. What about this KSI tool?
Yeah, this is another one. Like I already said, every time you mention blockchain, people think, oh, blockchain, this means Bitcoin. And Bitcoin is so-called proof of work-based blockchain system. And this type of blockchains, they really spend a lot of energy just keeping the thing going. And this is by purpose, by design. And the reason why Bitcoin blockchain uses this kind of proof of work is that it is an anonymous and unpermissioned network. Anybody can join the Bitcoin network and be a part of it, and be essentially take a service provider role in the network. And because anybody can anonymously do this, it is very hard to use any voting or any other identity-based consensus mechanism in these kinds of networks, because it is the digital identities can be cloned. Like the old saying is, on the internet nobody knows you are a dog. So you can just generate, if everything is anonymous, I can submit myself basically in multiple copies, and anything like voting wouldn't work because I could replicate myself and obtain more votes, more voting power. And this proof of work is designed to limit that. If I have to spend energy to cast my vote, then I cannot replicate it infinitely because I would need to spend more and more energy to get more and more votes. And this is essentially what happens in the Bitcoin network and why it burns so much energy. KSI is not an open unpermissioned network. We run the core servers. We know the identities of the core servers, and we know how many there are and how so we can do the consensus in the core network based on voting. And just counting digitally signed votes is not expensive operation, and therefore we don't need to burn this amount of energy. We just run the whole system. So the core network runs on 5 normal servers, nothing extraordinary. And the aggregation network, like I mentioned, this scales depending on the number of users. So as long as we have a reasonable load, also the number of servers is small, and we don't need to burn excessive amounts of energy. So this is not a concern here.
That is good to know. And we currently have one more question. You mentioned that so-called fingerprints of files are very small. That raises the question, how is it guaranteed that all those fingerprints can still be unique if there is, for example, a huge number of different files inputted?
Yeah, this is a very good question. So the background of this question is that if the inputs are of unlimited size, then there is essentially unlimited number of possible inputs to the hash function. And if the outputs are of finite size, then there is also a finite number of possible outputs. And this logically means that there must be sets of inputs where several different inputs map to the same output. And this goes against the idea of using the fingerprints as unique identifiers of the data or as representatives of the data. And the thing here is, the keyword here is that mathematically speaking, we are talking about infinite number of inputs versus finite number of outputs. But practically speaking, even with a rather small outputs, the number of different outputs is really huge. So KSI is currently using SHA-2 256 hash function, which has 256-bit outputs. This means that there is a 2 to the power of 256 bits different outputs possible. And so the probability, if you take 2 random inputs, the probability that those 2 random inputs collide is 1 over 2 to the 256. And this is so small a number that I really have no meaningful example or thing how you could make it feel how close to zero this number is. So for all practical purposes, this is an impossible event. And also, so this is against random collisions. So if you just take random inputs honestly and get a collision by accident, then probability of this is very small. And the cryptographic hash functions, they have also been specifically designed so that even if you go out of your way, if you try to produce a colliding pair of inputs, if you try to produce 2 inputs that map to the same output, this is extremely difficult to do. And you really cannot have much better chances of doing it deliberately versus just trying randomly. And so this is the answer. So the collisions, they technically and in principle they exist, but they are impossibly or infeasibly hard to find in practice, even if you try. And they are really improbable to happen by accident. So we are talking about probabilistic probabilities here, which are so low that that it's more likely that that the coin on your table spontaneously decides to jump up and flip over and fall back on the other side. This is more likely to happen than you just randomly finding a collision in a 256-bit hash function.
Okay, that is good to know. Currently, we have no more questions. So thank you, Ahto. And now I can present our next session. If I can share my screen. And the next session will take place on May the 3rd, and we will be talking about tools for data description and preservation. So please note down May the 3rd. This now concludes our webinar. If you have any questions, don't hesitate to contact us, and we will see you in May. Thank you very much.
Thank you.